First, I want to acknowledge some of those who were keen to be with us, but weren't able to speak, and it's a chance to get across some ideas as well about the ideas that they have represented in their career. First, it illustrates the breadth of activity in information theory and statistics. I want to remind everyone knows about histograms. Luc Devroy looked at it in the following way. He said, is it true that I can define a sequence of histogram density estimates, that is conditions on the cells, getting more numerous and narrower, such that for every probability density function f, the L1 distance from f to f hat goes to 0. And he wrote a book about it. Some of his work is joint with Gyorfi, who's mentioned there. And so interest arose. Ed took the charge of asking, well, what about the Kullback divergence? What can we say? We're not going to be able to get convergence for all densities because of the way Kullback divergence can be infinite. And there's another issue. If you look at dff hat, a histogram is 0 with positive probability in any particular cell. And you just made your divergence infinite. But Laplace told us what to do. You add 1 to each of the counts. It's Bayes optimal. It's even Bayes optimal with Kullback risk. And we were able to show that as long as you have some reference density G, that you know that your DFG is finite, then DFF hat will go to 0. And expectation and normal Shirley and things like that. And bless his heart, Ed was so keen that I talk about this. He even provided 12 pages of overhead. He's saying, please read this out. And that would have been nice, but we're not going to. But the content, I read it, it's well written, and the content is about that paper, okay? So if you're interested in learning more, then you can go to that paper. So thank you, Ed. If in any way you were watching a video of this, we're very grateful for your contribution. Now, the others are going to be part of another story that deals with the depth with which we go on a particular topic at this overlap of mathematics, statistics, and information theory. And I would say it has a long history. It really goes all the way back to Prony and Fourier. Prony said he wanted to model functions by linear combinations of sinusoids, but he wanted to adjust the frequencies to the target function. And Fourier came just a few years later and said, let's just include them all, equal spaced, multiple of the reciprocal of the period. And then he has this marvelous decomposition theory. And that's marvelous in low dimensions, but it sets back how you think about high dimensional approximation considerably. So in the advent of this computational age in the 1950s, statisticians have always been doing what we call term selection. When we run our regressions, we pick out the key features. But for a while in mathematics, it was being accepted that for good approximation, you should include all of the terms up to some degree. Sobolev norm conditions, it was the optimal thing. But in the hands of David Donahoe in the 90s, and even a little bit before Ron DeVore in the 80s, and others, there began to be developed a theory of nonlinear approximation. And the selection of terms in a linear regression, when you do that selection, it's no longer a linear function of your response. But selection then is a very important nonlinear ingredient. Well, you can think about what like a single hidden layer neural net does in the same way. It's a linear combination of sigmoids of linear combinations. As you learned from Max, there's just a close connection between sigmoids and cosines and sines. So what you can get with Fourier combinations or sigmoidal combinations are much the same thing. And what's then important about a neural net is the adjustment of those internal parameters, that is the selection of the sinusoidal basis functions that you're going to combine. And an analogous theory, neural nets are mostly thought of for high-dimensional situations. An analogous theory is for 1, 2, or 3 variables, where you would love to take advantage of the orthogonality of wavelet decompositions. And those of you who know the wavelet story realize how that really moved the story of linear projection type things away from just including all the basis functions. If you want to be optimal for certain function spaces, that is, you want to capture the local smoothnesses which are different in different parts of an interval, then you need to be selecting the wavelet basis functions. So selection, that nonlinear operation, is very important. So I think there was a transition historically at around that time. You can find the roots in work by Rafi Koifman and Mier and others even earlier, but it began to really impact the scientific world in the 1990s. So I am sure that if David or Ron were here, they would tell part of the story. I know you can't see all the details. As long as you can see the names in red, that's what I want. I just want you to see. Those who are curious will come up closer after and catch them. But if you're really that curious, you probably already know some of these things. I picked out ones like Donahoe, Vetterli, DeVroy, and Dobeshay. I see I misspelled Dobeshay, apologies. Data compression and harmonic analysis, IEEE information theory transactions. In the same year, Donahoe and Johnstone, minimax estimation by wavelet shrinkage. Those are 2 examples of many hallmarks of co-authored work by David Donahoe. And a recent one, neural collapse under mean squared error loss, proximity to and dynamics on the central path. Reading one of his recent papers, it's like, what if you trained a bunch of data using one of these generative models, and then you fit your generative model on the data that you have generated, and then it actually, you iterate and it falls apart. So David is helpful to us in being cautious about what these big networks can achieve. And I also want you to see for Ron DeVore, the 1990 paper I reference actually surveys work from the 1980s, as does the Acta Numerica paper from 1998. And then I reference one I did with them on approximation and learning by greedy algorithms, and we're going to say more about greedy algorithms. And Dobeshay, DeVore, and several others, long list. Here's an example that in 2023, neural net approximation of refinable functions. So refinable functions is the heart of what a wavelet does. So there's these eminent scholars are connecting the neural net story and the wavelet story. So that's fun. Okay, but then what do I think about this stuff? Well, as I said yesterday, a lot of my time is spent working with students. So rather than putting up slides of giving equations and theorems and so on, I'm just going to list some students. And under 2 headings, mixture density estimation and greedy neural net methods. So mixture density estimation, there had already been the greedy algorithm stuff you can hear more about with Lee Jones. You heard more about it from Jason Klusowski. It was mentioned also by Max. So that's the idea in the greedy neural net training. You've already fit 80 neurons, and now you want to fit the 81st. So you take the residuals of your fit, and or another way of saying it, you take the previous fit and you take a linear combination of that with a new neuron, and you choose the parameters of the new neuron to optimize that. And the paper with Barron, Cohen, Dahmen, and DeVore is an example of a paper in a line of dozens that contributed to saying what are the approximation and risk properties of that type of procedure. And with Jonathan Lee, we extended it to like Gaussian mixture estimation. You want to model a density as a linear combination or convex combination of several Gaussians. You've already fit several. You want to put in one more. You would like to iteratively improve your log likelihood, and we proved similar greedy approximation and risk bounds for that. But in my mind, anyone who's talked to me through the years knows that what I care about most is not just being able to say you could have a greedy algorithm, because it's not yet really an algorithm. Because when you're in high dimensions, even picking just one direction, the internal parameters of one neuron are the centers of one Gaussian to linearly combine with the others. We don't know how to do that provably well. But there's a lot of expertise here, and the students and you guys, and I think conditions under which this can be done well can be illuminated further. I know they're negative results, but I'm an optimist that is suitable, with high probability statements or conditions on the parameters or the smoothness of the sigmoids, things like that, or the approximate optimization rather than exact optimization by probably some sort of posterior sampling method will be successful. And that's represented in that list. Lots of Yale theses have been written with various theorems, lots of good results, none of them going all the way to what I'm asking for. But it shows you how I have occupied my time with these students trying to push for that. Lots of good ideas in there. And my apologies, there are several other students that are here, and your work has been great too. It's just not on this topic. And okay, so the latest is with Curtis. Curtis, are you here? Yeah. So we're hopeful. We're pushing hard on it. We have an acceptance at the ISIT, and we put a conjecture in it. We're working feverishly to try to prove, and indeed, it's a clever idea. When you take the log likelihood or pseudo-log likelihood term that would arise when you're fitting one more neuron, the problem is it's not a convex objective function. But if you were to add a big enough multiple of a square, it would be convex. Okay, and we're talking about up in the exponent, a log likelihood thing. So what if you could center that square you're adding anywhere you like? All right, so you can center at some u. Now, take the result of putting a distribution on u and integrate that out, and you end up with a way to marginally have the distribution you want. So you have an auxiliary variable, and we have a cute way of getting a log concave coupling. The conditional distribution of the parameters given u is log concave. The density of u, given the parameters, are conditionally independent and easy to sample from, and we're exploring the extent to which, based on those, we could have a sampler. So I will continue this quest. So you hear I'm retiring this year, but that's so I can keep working on this.